YOLOv9 is out and it's beating out the competition in both speed and accuracy. The creators of YOLOv4, YOLOx, and YOLOv7 have released new model and according to the paper is new state of the art in real-time object detection. In this video, I'll show you how to run the inference using pre-trained COCO weights, train and evaluate the model on custom dataset, and deploy the YOLOv9 model using inference package. So, without further ado, let's dive in. The link to the notebook I'll be using is in the description below, but you can also find it in RoboFlow Notebooks repository. I strongly encourage you to open it in separate tab and follow along. We navigate into Models section and search for YOLOv9 Object Detection Notebook. Then click Open in Colab button, and after a few seconds, we should get redirected to Google Colab page. Before we start, we need to make sure that we have access to GPU. It is especially important if we plan not only to run the inference, but also fine-tune the model on custom dataset. This process can be unbearably slow in CPU-only environments. To do this, we scroll slightly down into Before You Start section and execute NVIDIA SMI command. This command will only execute successfully in GPU-accelerated environments with NVIDIA GPUs. If your result is similar to mine, then you're probably good to go. However, if you see a message saying that NVIDIA SMI command is not recognized, it probably means that you do not have access to GPU. In this case, click Runtime and from Extended dropdown, select Change Runtime Type, then choose version with NVIDIA T4 GPU. The next step is to clone YOLOv9 repository and install all necessary libraries. Unlike YOLOv8 and YOLONAS, YOLOv9 is not distributed through pip package, at least at the time of the recording. This means we need to clone the repository and manually install all dependencies. After installation, instead of CLI or SDK, we'll have a set of scripts to detect, train, evaluate, and export the model. The project structure is quite familiar to the one known from older models like YOLOv5 or YOLOv7, so if you have any experience with them, you should feel quite familiar. If you don't worry, I'll still guide you through the whole process. Additionally, to make our life easier, we'll also install RoboFlow pip package. It will allow us to download the dataset in format compatible with YOLOv9. I will use the football player detection dataset, but you can download whichever you like. There are already more than 500,000 datasets on RoboFlow Universe. The links to both Universe and my dataset are in the description below. Unfortunately, YOLOv9 lacks support for automatic model weights download. You can download them manually from GitHub, but inside the notebook you'll find a set of commands allowing you to do that automatically. So let's run them now to finalize the setup process. Our next step is to run inference with pre-trained COCO weights. I think it's a great way to get familiar with new model, and at the same time it will allow us to confirm that the installation was successful and everything works as expected. To test the model, I will use the image of my dog, but if you want to run it with your data, simply drag and drop your image into the left panel of Google Colab and replace the source image path value with path leading to your image. As I said before, YOLOv9 does not have dedicated CLI or SDK, so to perform the inference we will need to use detect_py script. The most important arguments that we need to provide are weights and source. The first one is simply path to weights file that we already downloaded from GitHub. The source can be a path leading to individual image or video, but also to the whole directory with multimedia files, or if you run locally to webcam stream. On top of that, we will set values for two extra parameters, confidence threshold and device. I set the confidence threshold at 0.1 because I want to capture as many detections as possible, even those that the model is not entirely sure about. The device specified the hardware we want to use during the inference. We could pass the CPU here, but given that we have a GPU, we'll pass the CUDA device index, in our case 0. Now let's run the inference using two architectures and compare the results. The commands we will use are almost identical, the only difference lies in path to model weights. Let's start with gelan-c. By default, YOLOv9 save inference results in YOLOv9 detect exp directory. We can override this behavior by passing custom values for project and name arguments. Now, let's run the inference for YOLOv9e and compare the results. This time, the results of the inference were saved in exp2 directory. We can see that using the same parameters, YOLOv9e is capable of detecting more objects in the same image. And that's consistent with the performance reported in YOLOv9 paper. Last week, we had our first community session where we discussed YOLO World, a almost real-time zero-shot object detector, and I would like to use this opportunity to thank to everyone who joined the stream. I really had an awesome time meeting you all and answering your questions. We decided to continue this initiative, so if you have any questions about the code or demos that I will show today, or about YOLOv9 in general, make sure to leave them in the comments and I will make sure to answer all of them during the upcoming stream. And of course, it would make me even more happy if you could join it live. You can find more details along with exact date and time in the description below. And once again, thank you. Okay, we know how to run YOLOv9 using pre-trained weights. Now it's time to learn how to fine-tune the model. But before we can do that, we need to prepare our dataset. As I mentioned earlier, I will train my model on football player detection dataset. If you'd like to try a different one, feel free to browse through Universe and pick one that seems interesting. Then, from left panel, select Dataset and click Download Dataset button. When the pop-up window appears, pick the export format, in our case YOLOv9, make sure that Show Download Code option is checked and click Continue. After a few seconds, a code snippet will be generated. You just need to copy and paste it into Google Colab and you're good to go. I, however, will stick with my original choice. I just press Shift-Enter and once it's done, I see a prompt asking me to provide RoboFlow API key. I follow the link that takes me to RoboFlow website, I click Generate Token, copy it and then return to Colab, paste and hit Enter. The downloaded dataset is divided into three subsets: Train, Validate and Test. The Train and Validate subsets are going to be used during the training, while the Test subset will be used for evaluation. Remember that the test set should not contain any images that were used during the training. Each part consists of two directories, one containing images and the other containing labels. Each label file is essentially a txt file in standard YOLO format known from earlier versions of the model. Each line describes a single bounding box and consists of 5 numbers separated by spaces. The first one is the index associated with the label. For example, for COCO dataset, index 0 is class person. The other 4 are relative coordinates describing the position and dimensions of bounding box in the image. Now that our dataset is ready, we can finally start the training, and to do it, we'll use train.py script. This time, however, we need to specify a lot more parameters. Let me briefly introduce you to the most important ones. Let's start with arguments typical for any computer vision model training: batch size, image resolution, and epochs. This affects the amount of GPU memory required during the training, as well as the total time needed to complete it. Batch size regulates how many images pass through the network simultaneously. It should be as high as possible, naturally limited by the amount of available memory. Before entering the network, all images must be scaled to a common size, which is defined by image resolution. The higher the value, the smaller objects we'll be able to detect. Unfortunately, this also means increased memory usage and longer training time. Epochs define the number of training iterations. It's usually a matter of intuition. It needs to be large enough so the model has time to learn, but not too long so overfitting wouldn't occur. Data defines the path to YAML file specifying the structure of our train set. Finally, weights and config indicate the checkpoint and architecture we would like to use during the training. In this tutorial, we will train the smallest architecture available in YOLOv9 repository, GLAN-C. It's time to press Shift plus Enter and get it going. The training process can take time, so let's use the magic of cinema to speed it up. After several minutes, our training was completed. Now it's time to evaluate the model and check how it performs with object detection on new images and videos. Model evaluation is a must-have after fine-tuning the model on custom dataset. After all, we need to understand the strengths and weaknesses of our model and check if there are any differences in accuracy across different categories from our dataset. Let's start by going through the directory storing the training artifacts. Inside, besides weights, we can find several visualizations that will help us understand the progress of training session. Let's start with the graph showing change in key metrics over time. The 6 charts on the left display various types of loss function calculated for both the train and validation sets. These charts are an excellent tool for detecting overfitting. All of them are expected to decrease as training progresses. However, when a model is trained for too long, the validation loss function often tends to increase, signaling that the model is too closely fitted to images from the train set. In our case, it's clear that the model could have been trained for much longer without any issues. The charts are still steeply decreasing, and there is plenty of room for further optimization. The remaining 4 charts are various metrics such as precision, recall, and MAP, and their values should increase as the training progresses. The next chart we can analyze is the confusion matrix. It shows how often objects of different categories are confused with each other. I like this chart because it allows us to delve deeper into model's characteristics. In our case, we can clearly see that the model excels at detecting players, referees, and goalkeepers, but performs significantly worse at detecting balls. YOLOv9 provides another useful visualization, this time focusing on label distribution. We can draw deeper conclusions by analyzing both of these charts simultaneously. We see that our dataset is unbalanced, with player class being significantly overrepresented. Hence probably the best performance of the model in detecting players. The ball class performs the worst, not only because it appears the least frequently, but also because the bounding box sizes for this class are the smallest. Since we decided to train our model using 640 input resolution, such small bounding boxes might simply be scaled down to a tiny group of pixels, possibly not carrying enough information to reliably detect the ball class. Now let's benchmark our model using val.py script. As expected, both recall and MAP for this class are significantly lower than average. This is likely to a high number of missed detections. A solution to this problem could be training the model using 1280 input resolution, but as mentioned, the training session would then be slower and require more GPU memory. Okay, it's time to put our newly trained model to the test and see how it performs with previously unseen images and videos. The command does not differ much from the one we executed at the beginning of the video. We switched the path from the model pre-trained on COCO dataset to the one we just fine-tuned, and as the source, we passed the entire directory containing the test dataset. Let's take a look at some of the results. As expected, the model performs relatively well. The biggest issue is reliable ball detection, where we encounter both false negatives and false positives. Double detection also occurs frequently when a referee is simultaneously detected as both a player and a referee. Now, let's have some fun and see how our model handles short video clip. So how do we deploy the model that has no SDK? We can certainly try to hack a solution based on the detect py script available in the repository. However, it seems that a much better and certainly more robust solution would be to use RoboFlow to manage your weights and deploy the model anywhere you want. It's super easy. You can do it in few lines of code. Let me show you how. We start where we left off with our model already trained in Colab. First, we need to install two additional packages, Inference and Supervision. We will use Inference to deploy our YOLOv9 model locally, but you can use it to run all sorts of different computer vision models. Supervision is a computer vision Swiss Army knife that this time we will use for annotating our inference results. Now we use the deploy method, specify the model type, in our case YOLOv9, and the directory containing the training results. This will send the weights to RoboFlow and enable us to use them both for running the model locally and through the API. Now let's try to load the model back into the inference. We specify the model ID, which is the end part of the address displayed above, the project name / dataset version, and we pass our RoboFlow API key. To get your RoboFlow API key, you need to log into your RoboFlow account and then by expanding the dropdown in the upper right corner, go to Settings. From the panel on left side, select Workspace and go to RoboFlow API section. Now you can simply copy your private key, return to Colab, paste it and press Enter to initiate model download. Once the model is loaded, we can choose a random image from our test set, load it using OpenCV and run it through the model. Finally, using Supervision, we visualize the result. Since Supervision offers a variety of different annotators, we can choose something more suitable for our use case. For example, the ellipse annotator. Funny how such a small change can make the results seem much more interesting. At the end of last year, we released a video covering my favorite object detection models. The goal was to evaluate popular detectors not only in terms of speed and accuracy, but also take into account less obvious criteria such as community size, ease of use, and licensing. I mentioned that the higher accuracy of the base model on COCO dataset does not always translate into higher accuracy of the fine-tuned model, and that the accuracy of detections is usually more affected by the quality of the dataset that was used for training than the choice of specific architecture. Assessing YOLOv9 from similar perspective, it's worth to mention that it is still a very young project. Although, according to the paper, it has managed to beat the competition in terms of speed and accuracy, on the other hand, it has no SDK, no CLI, and no documentation beyond the GitHub README. So to sum it up, I encourage you to try YOLOv9, train your model, deploy it with Inference. However, keep in mind that there are still plenty of other popular object detectors that might be just a little bit slower and less accurate, but still be a valuable alternative because they have large community, great documentation, and a lot of examples online that you can use to build your own project. Of course, a powerful real-time object detector can be applied in many scenarios. In this tutorial, we trained a model for detecting players on a football field, but YOLOv9 can be just as well used to power smart self-service checkout. The customer simply needs to move the product in front of the camera and it is automatically added to the bill. I also encourage you to check our Hugging Face space where you can upload your image and compare YOLOv8, V9 and YOLONAS side by side. We are using models pre-trained on COCO dataset, so detection is limited to only 80 classes. If you want to go beyond that, I encourage you to check our YOLO World space where you can detect any class without any training. And that's all for today. If you liked the video, make sure to like and subscribe and stay tuned for more computer vision content coming to this channel soon. My name is Peter and I see you next time. Bye.